here's how I would set it up. Okay? I would let TF be the final temperature. We know that the alcohol is going to warm up and the water is going to cool down. We know that the alcohol is going to warm up more than the water cools down because there's less mass of alcohol and it takes less energy to change a given mass of alcohol by a certain temperature than it does the same mass of water. And of course we know that the specific heat of water is about 4.2 joules per gram Kelvin, right? Kind of an average between 0 and 100 Celsius is about 4.186 joules per gram Kelvin, okay? But that varies from about, I don't remember exactly, something 4.16 something up to 4.19 something. There's that much variation for liquid water. Okay, so anyhow, we have these, so well, here's the temperature change of the alcohol, here's the temperature change of the water, right? So, now we're going to use delta Q for the heat required, for the energy you have to supply to the alcohol or take away from, depending on which direction the temperature is going. So, delta Q of the alcohol is going to be what? It's going to be 2.4 joules per gram Kelvin times 80 grams times delta T of the alcohol, right? And delta Q for the water is going to be 4.2 joules, and these are approximate, per gram Kelvin, times 100 grams, times delta T of the water. Now, we're assuming that there's no contamination from the room, that the room doesn't gain any heat from the system, and the system doesn't gain any heat from the room. From what we saw in lab, you know that the temperature changes are relatively slow if you have either of these things in the room, right? Now for the water, it's a lot faster than it is if it's up at 80 degrees than it is at 30 degrees, let's say. But you know that, okay? Now, we're going to be able to mix this alcohol and water almost instantly, right? Pour the alcohol in, it's all mixed within a couple of seconds.
Are we starting with the alcohol at 30 Celsius or 20 Celsius?
20?
Should that be a minus 10 Celsius?
I got the 10 from over here. No, it should be minus 20. That's where it starts. Okay? Thank you. Glad somebody's paying attention to little details.
Huh.
You know, last thing my eye saw was 10 Kelvin. So, yeah. Okay? You got to watch me. I'll do that. Okay, so we have this, right? Now, I'm not going to complete this. I'm just going to say that since there's no significant time for the temperature to change, for the system to exchange heat with the room, that whatever this gains, this loses, right? So there's no heat exchange with the room. Meaning delta Q total is 0. Okay? So, total is 0. Okay? Well, you can write that, you know, I mean, you can use these expressions for your delta T alcohol and delta T water. Just write it out and solve it for delta T, right? Keep track of your units. You'll see that your units do come out in Celsius degrees. And I mean, you know, each of these expressions is in terms of TF and given quantities, okay? So you immediately get a solution, okay? And what we're doing here is we're actively working from the principle of energy conservation. No energy exchange with the room or the surroundings means that energy is conserved within the system. Therefore this. Now in a real case, if you're mixing not alcohol in water, but let's say a chunk of hot steel in water, it takes a little while for that steel to come to thermal equilibrium. And if the system isn't isolated from the surroundings, then there is going to be some significant exchange between the system with the steel and the water and the surroundings. It won't be an isolated system. Okay? We can treat this as an isolated system. Other systems, we do have to consider whether the system is to a sufficient degree isolated. If not, you got to then worry about the thermal exchange, and we're going to worry about that with what we've got in lab. Okay? We're going to see to what extent the thermal exchange with the room might be significant, because we took enough data to get a handle on that. Okay? So in any case, in this case, and in the ideal case in calorimetry, where you either do something really quickly, get the thermal exchange that goes really quickly, or put the thing in an insulated container, okay, a calorimeter, or in some other way isolate it from the surroundings, then you can approximate everything as the ideal case, where the system is isolated. Okay?